So for our values of the mean, mu, and standard deviation, sigma, in terms of a graph for this distribution, in terms of a bell curve, we always have that the mean mu occurs in the middle / at the top of the distribution, and then along that curve we see one standard deviation below and one standard deviation above occurring at the inflection points of the curve. And for those of you who know a little bit of calculus, you're a bit familiar with the idea of an inflection point, but roughly speaking, the inflection points of a function are the places where it goes from curving up to curving down, essentially. But really, with any normal distribution, the best thing to do to understand what's going on is to think in terms of some pictures to develop a better intuition for the overall situation. So looking at these, in the first case, we have inflection points that land at 2 and 5. As you can see, that's where the curve starts to come back around. So the standard deviation, since we have that mean in the middle of 3.5, would be about 1.5. For the second case, we can see that that curve is taller. Now, it's easy to look at these curves and assume that because one is taller, that means it has a higher mean. That doesn't mean the mean is larger. It doesn't mean the mean blah, blah, blah. It means that the center, the mean in this case, occurs more often. So for that one, we have a mean of 3.5 and a standard deviation of 0.7 at those inflection points. So you can see there that by reducing the standard deviation, we made the curve taller because there's less variation overall. And then in that last case, we just take a bit more off on our tail to the right because, well, technically, this curve goes on and on and on forever and ever and ever. You know, we have that our mean has to be some positive value and the standard deviation has to be some positive value, but nothing that says we have to focus just on that space. We can take our window as wide as we like to, which causes some problems in reality, but we're going to worry about that in section 5.2. Anyway, to help better understand what's going on with these cases, we're going to look at an example. So for the two normal curves graphed below, we want to determine which has the higher mean and which has the higher standard deviation. So again, looking at these curves, there's probably some, that's what I'm looking for, instinct that you see A is taller, which means it must have the higher mean, but that's actually not helpful in this context, in terms of the mean anyway, because what we want to see for the higher mean is really its position horizontally, that it's further to the right. For this one, we would have that A has the higher mean, where in this case, the comparison would be something like 15 for A and 12 for B. It's a rough estimation. On the other hand, because B is flatter, it's wider, and a wider normal distribution indicates that we have more variety, indicates a larger standard deviation. So B, because it is flatter, has the wider standard deviation. And be careful with this sort of estimation that you pay close attention to the scales of the graph. Here we can sort of see that the standard deviation there should be somewhere between 2 and 4, maybe. It's kind of hard to tell just eyeballing it, but it's very easy to take a curve like that and just pull the scale for one of them to make it seem like they're about the same. So always pay close attention to what's going on in that bottom section. Usually when I draw these, I'll try to draw them with the same general shape, which means you might think that they all behave kind of the same, but that scale is really what tells you the actual behavior. And the next thing we're going to look at here is one very special, very important type of normal distribution, the standard normal.